So, today we start with everybody's favorite concept, that of acceleration. And I know that people seem to find this very hard, but it is actually not that complicated. And once you understand the basic idea, you should be able to work out most of this. Now, unfortunately, I don't know why my car gets stuck with my title. So when I move the car, title's gonna move. Maybe a little bit. Am I confusing you? Am I making you dizzy? I hope not. Anyway, so here's my car, and it's going at a certain speed. And instead of just going at a certain speed, imagine that it starts getting faster and faster and faster. Now we say that its motion is accelerated. But that's not acceleration. Going faster is not acceleration. Acceleration is just exactly how much faster am I going every second. That's what acceleration means. And we can make this very, very precise. So imagine that I have a certain speed v. Now, if my motion is accelerated, after a certain time, my speed will have increased by a certain amount, increase in v. Remember, this thing here means increase. So let's say in 2 seconds, my speed increased in 8 meters per second. Now, the acceleration is just how many meters per second my speed increased every second. So all I need to do is say, okay, so here's my increase in v. How long did that take? Well, a certain increase in t. And that's my definition of acceleration. So acceleration is just the increase in velocity over the increase in time. And this is the definition of instantaneous acceleration. If I want the average acceleration, all I need to do is to take this increase to be very large. If I want the instantaneous acceleration, I take this increase to be very, very small. Now, let's see an example so that you see that this is not such a big deal. Now, my car is initially moving at 2 meters per second, and after 3 seconds, it's moving at 8 meters per second. Right? So what I want to know is how many meters per second faster does it move each second? Well, in 3 seconds, it managed to move 6 meters per second faster. So each second, it gained a speed of 2 meters per second. So it's moving 2 meters per second faster each second. So its acceleration is 2 meters per second per second. Now this thing that I did with my head, I can do with math. So the increase in speed is just final speed minus initial speed, because increase always means final whatever minus initial whatever. Okay, so let's calculate the increase in speed first. Increase in speed is final speed minus initial speed, and that's 8 minus 2, and that's equal to 6 meters per second. Done. What's the increase in time? Well, the increase in time is just the time that it took me to do this, and that's just 3 seconds. And now all I need to do is to plug this in here. So let's do that. So that's equal to increase in speed. We said that it was 6 meters per second. The increase in time was 3 seconds. And then I get 2 meters per second every second. 2 meters per second every second. And of course, I'm not going to write down the units like that because that's ugly. So I'm going to write it as 2 meters per second squared. And these are the units of acceleration. However, in the IB, people don't like to express the units like this, because we always like everything to be multiplying. Now, how do we get a power that's dividing to be multiplying? Well, if you know anything about powers, you should know how to do this with your eyes closed. But just in case, I'm going to show you. Acceleration is 2 meters second to the minus 2. So instead of writing divided by second squared, we just write times seconds to the minus 2, and this means exactly the same thing. So that's the definition of acceleration, and if you understand this basic notion, everything else will be a lot easier. If you're shaky with this basic notion, then you're going to struggle for the rest of the year. So please, if you don't understand this, replay this. Figure it out yourself. Get a pen. Start, making numbers, whatever it takes until you understand this notion. Then we can start building on this. One more thing. What if instead of an increase in velocity, I have a decrease? So my car goes from 8 meters per second to 2 meters per second. Well, easy. Now I can calculate my increase in exactly the same way, right? My increase will be just final velocity, which is 2, initial velocity, which is 8, and then I'm going to get minus 6 meters per second. So then this means that my acceleration is going to be minus 6 meters second minus 2. So when the velocity doesn't increase but it decreases, I still have an acceleration, it's just negative. Sometimes we call that retardation or deceleration, but actually it's just acceleration. A movement that's decelerating is really accelerating at a negative rate. So it's the same thing. We don't need to change anything. This works for both positive and negative increases in velocity. Negative just means that instead of going faster, we're going slower, or we're going faster but backwards. Okay, so now it's time to revisit motion graphs. And now that we have acceleration, things have become way more interesting, and that's great, because otherwise it's boring. So we're going to, again, look at velocity time graphs and displacement time graphs. Now, when there's acceleration, this means that our velocity is always increasing or decreasing by the same amount. So we're going to take the simple case of a stone falling. Now, in the case of a stone falling, well, imagine that I'm right here. Here's my stone. First thing, I throw it up. I don't throw it up. I mean, I throw it upwards. Just that would be weird. So at 20 meters per second. And then my stone is going to first thing slow down, then stop, then speed up, but downwards. And always at the same rate, and the rate is the acceleration of gravity. And remember that the acceleration of gravity is minus 10 meters second to the minus 2. And it's minus 10 because it points downwards, and we decide by convention that plus is up, minus is down. Okay, so let's draw this. So here's my velocity. I'm going to say that this is 10, this is 20. So I start at 20 meters per second. And after 1 second, so this is 1 second, 2 seconds, 3 seconds, 4 seconds, and so on. So after 1 second, I'm down here at 10 because I lost 10 meters per second, because this is telling me that every second I lose 10 meters per second. So from 20 to 10. And then after the following second, I'm going to lose 10 meters per second again. So you can see that this is a straight line because each second I lose exactly the same amount of meters per second. And I can just make a straight line that goes down like this. And then what happens? Is this going to rebound? Is this going to stay here? What is it going to do? Pause the video, give me an answer, and let's see if you got it right. Okay, so hopefully you paused the video, you thought about this, and you thought that, well, since first it's going up, the velocity is positive, then later it's going to go down, so the velocity is negative, so this will keep going down further and further and further. So this will do this, this, and this. So we will have a straight line that goes down. Now here's the really funny thing, which is that I can actually use this graph to calculate acceleration. So imagine that I didn't know this. So I don't know that g equals minus 10 meters per second squared. And all I have is this graph. How could I figure out that the acceleration of gravity is 10 meters per second squared? Well, all I do is go like, well, here's a triangle, and in 1 second, the decrease in my speed was 10. So my speed decreased 10 meters per second in 1 second, and that's 10 meters per second squared. Done. So as you can see, I calculated this. How do we call this thing here? Dividing this thing, the rise over the run, which is 1 second. Pause the video and tell me how we call this. Okay. Hopefully you said that we call this the gradient. And you would be right. The way to calculate the acceleration from our speed time graph or our velocity time graph is just by using the gradient. The acceleration is just the gradient of the speed time graph, just like the velocity is just the gradient of the displacement time graph. Now that we know this, we're in a position to actually do a speed time graph. And the first thing that we need to think is, well, at the beginning my stone is at 0.0, which is my hand. And then it goes up, but slower and slower and slower. So it will do something like this. Exactly the shape that you would see if you threw the stone, right? if you throw it forward, for example, it will do something like this. And then afterwards is going to start going down faster and faster and faster. So we will do something like this. So we can draw this graph, and it's something like this. And that's how this kind of motion looks like when the acceleration is negative. When it's positive, things are different. Again, could I calculate this thing here, for example, this displacement here, from this graph? And the answer is yes. The same way that I told you that the displacement was the area under the VT graph in the other case, it's also going to hold up now. So if I zoom out, imagine that I have, here's my graph. I'm going to make it a little bigger. Let's say this is 20, let's say this is 0, and I want to find my displacement after 2 seconds, so this is 1, 2 seconds. Then all I need to do is calculate the area under here. And the area under here is, of course, the area of a triangle. If you don't know how to calculate the area of the triangle, well, that's really bad. But remember that it's just a square divided by 2. So the area here will be, so the displacement will be the area under this, which is 20 times 2 over 2, and therefore that's equal to 20 meters. Bear in mind that I did not multiply velocity and time. What I did was get the area under the VT graph. In the IB, you will almost never, ever get displacement by multiplying velocity and time. That only happens when velocity is always the same, and that hardly ever happens. So you need to remember that velocity is the area under the VT graph. Now what I'm going to do is use this VT graph, which is generic. I'm not going to plug any numbers in this, to derive a formula that will allow me to calculate the displacement given the initial velocity of a movement that I'm going to call v0, the acceleration that I'm going to call a, the time, and the initial displacement, which I'm going to call x0. And the way I'm going to do this is just by using the fact that the difference in displacement is the area under this graph. Okay, so let's see how we do this. Well, all I need to do is figure out that this is, so let me just close this area. I need to calculate this area over here. I have a certain body that has an initial velocity, then it accelerates at a constant rate until it reaches some final velocity that will depend on the acceleration and the time. And it accelerates for a certain time t that I don't know, and I don't care. I'm going to do everything in terms of letters. I'm not going to use a single number, because remember, this is the IB, and every time that we can, we work with letters. So I'm just going to write VF here, though I'm not really going to use this too much. Alright, so what I need to figure out first is that I can divide this area into two parts. One is a little rectangle, that's really easy to calculate, and the other one is a triangle that goes from here to here. So I'm going to split it in two. So the increment in my displacement, the increase in my displacement is going to be just the sum of these two areas. So let's write that down. I have that the increase in my displacement is going to be this little area here, and this area here is really easy to calculate. It's just v0 times t, right? Base times height. So v0 times t, and then plus this area here. And for this area here, what I have is this height here is Vf minus V0, right? And Vf minus V0 is nothing but the increase in speed. So Vf increase in speed times the base, which is again t. So plus increase in speed times t. Cool. Now, careful. Am I done? Did I get this right? Pause the video and tell me. Okay, well, hopefully you realize that this is not correct, because that's the area of a rectangle and this is a triangle, so I need to divide by 2. So increase in v times t over 2. But I don't want any increase in b here, because this means that I will have to calculate it every time. I want everything in terms of a and t, so that I don't have to do any intermediate calculations. I want everything in one formula, no intermediate calculations. So I need to express increase of V in terms of A and T. Thankfully, this is very easy to do, because I know that A, that's the definition, is just the increase in V divided by the increase in T, which in this case is just T. So the increase in V is just A times T. And now all I need to do is plug this thing in here, and I'm going to get the formula for the increase in displacement. I'm going to get V0t plus AT. So I have this t and this t. So t times t, that's t squared. So t squared over t over 2. Now, of course, that's only the increase in displacement, but I want the displacement. So this means that my displacement is going to increase this much, but I may have an initial displacement. For example, I could already be 10 meters away from the origin. So all I need to do is replace this by its definition, which is the final displacement minus the initial displacement. So let's do that. First, let me zoom in so that we have a little bit more space. We're going to have that final displacement minus initial displacement, which is just increase in displacement, is equal to V0t plus 1/2 AT squared, and that's just rewriting this so that it's prettier. And then all I need to do is to put this over here, adding up. If you don't know how to do this stuff, again, this is the IB, this is not cute anymore. Come and see me, and we need to work this out before it's too late, because you need to know how to solve equations, especially if it's just adding up. Anyway, here's our final equation that I deduced just by looking at the graph. This means that you can do this too. If you know that the final displacement is just the area under the VT graph, then you know how to deduce this formula anytime you need it. And actually, you don't even need to deduce this because it's in your data booklet. But the main point is that if you understand things properly, all this stuff that we've been doing can be deduced in an afternoon. No problem. And not only this, you should be able to do this on your own. If you really understand things, you should be able to do this on your own. So my recommendation after watching these videos is that you stop it, you get a piece of paper, do not look at my video at all, and try to rededuce this formula on your own, see if you can do it. Because it will be a very good exercise for you. You will get a lot more understanding from doing it yourself than from watching me do it. Alright, so that's all for today. This is what you should be able to do after this video. You should be able to define acceleration and define, not using words, using formulas, because that's how we define things in physics. Words are for biologists, formulas are for physicists and mathematicians. You need to be able to calculate acceleration using its definition. That's the bare minimum. You need to be able to calculate acceleration as the gradient of the VT graph, and that's a classic exam question, both in standard and higher level. Then you need to be able to calculate the distance as the area under the VT graph, and again, that's the bare minimum that you need to be able to do in order to just barely scratch a pass. And you need to be able to apply the final displacement formula that we just derived, and ideally you should be able to derive it yourself. Okay, well, now you're ready for a new batch of problems. These ones are going to be way harder than the ones from the other day. It's fine. We're going to get, at the very least, 2 full lessons of practice for this, because I want this to be extremely clear before we move on to even harder stuff. Good luck.